We are now going live with our webinar. Welcome to those of you joining us today. We're going to give just one. All right, we'll go ahead and get started with our webinar today. This webinar is going to run for 1 hour. It is an interactive webinar where we have a panel of experts here today that have joined us. We're so glad they're here. We'll be talking about InSAR for mining applications. And during this webinar, you'll be able to ask questions to our expert panel all along the way. This webinar is brought to you by the Geotechnical Center of Excellence at the University of Arizona. If you are unfamiliar with the GCE, we are an industry-funded center. We are member-led, and we are interdisciplinary. What we do is collaborate with industry professionals and academic professionals to provide geotechnical research and education to the global geotechnical community, with the goal of bridging gaps within and between academia, industry, and fields of study. If you'd like to know more about the GCE, please feel free to send us an email. We'd be happy to share more with you. And as mentioned, the GCE is a member-led company and industry-funded. So here on our screen are some of our, all of our members that we would like to make sure we say a big thank you to. Without their support, events like this would not be possible. So we thank them for providing support to the GCE so that we can put on our professional development courses, do our research projects, and provide webinars such as the one that you're in today. So thank you so much to the member companies. And a note that the some of the presenters that are here today on our expert panel are also within our Geotechnical Radar Monitoring course, which is an online on-demand professional development course. It's currently running on the GCE's learning portal. If you're interested in learning beyond today's webinar more about not only satellite-based SAR and InSAR, but also on ground-based radars and how to use radars at your site, the capabilities, limitations, how to interpret data, and real-world examples and case studies. Please use this QR code here if you're interested in registering for this course. I'll show this again at the end of the presentation today in case you miss the QR code. All right. And now to introduce the team who's here today. So we have from the GCE, our webinar team today, myself, I'm Jillian Noonan. I'm Senior R&D Engineer with the GCE, and I'll be acting as your moderator today. And then alongside with me, I have a great team from the GCE. I have Julia Potter, who is co-director of the GCE. Julia, thank you for being with us today.
Thank you, Jill, and thanks to the attendees for being here and to the panelists for sharing their knowledge. I think it'll be a great discussion.
Also joining from the GCE team is James McNabb, who is Senior R&D Engineer. Hello, James.
Hello, everybody.
And Allison Brucey, who is our Program Coordinator. Allison, thank you so much.
Thank you, Jillian. Thank you, everybody, for being here.
And we'll be working to sort through questions that are submitted by our attendees today. So the team will be working alongside myself, who will be moderating our panel discussions today. And now I am honored to introduce our expert panel, who have contributed their time to this webinar today to answer your questions. Firstly, we have Jon Leighton, who is Director of Operations with 3V Geomatics. Jon is an experienced InSAR expert with 7 years of academic InSAR experience and 12 years commercial InSAR experience with 3VG. Following his InSAR-focused master's and doctoral degrees at the University of Nottingham, he worked as a postdoctoral research fellow and lecturer in InSAR and geodesy. He joined 3VG in January of 2012 and has processed and managed many InSAR projects over a wide range of applications. Jon has conducted InSAR-related fieldwork at sites in the US, South America, and Africa, as well as many remote communities in the Canadian Arctic. Prior to academia, Jon had a 15-year career in the British Army as a geodetic surveyor, planning and conducting fieldwork for major geodetic projects worldwide. And Jon, thank you so much. Amazing background that you have. Definitely an expert. We're so glad to have you with us. Thank you so much.
Hi, everyone. Greetings from Vancouver.
Next on our panel today, we have Paolo Farina. Paolo is the Managing Director for GeoApp. Paolo holds a PhD in geosciences, a master's in engineering geology, and is a chartered engineering geologist. He's currently managing GeoApp, which is a service and consultancy company he founded in 2015, which is focused on geotechnical risk assessment for mining, natural hazards, and infrastructure projects. Paolo's specialties are monitoring technologies, early warning systems, and risk assessment, with a focus on integrated data analysis and interpretation. He's a member of geotechnical review boards of several large open pit mines in the US, Chile, and Peru, and was involved in 2019 following the collapse of the Brumadinho tailings dam as an independent consultant supporting the review and interpretation of the monitoring data collected before the collapse. Prior to founding GeoApp, Paolo worked for IDS, where he created and managed the mining business unit, as well as served as assistant professor of engineering geology at the University of Firenze, and prior to that was a visiting scientist at the Massachusetts Institute of Technology. Paolo's scientific work has around 3,000 citations and more than 60 publications in international peer-reviewed journals. Amazing. Paolo, we're so glad you're here. Thank you.
Thank you, Jill, for the great introduction, and hi, everyone. Greetings from Firenze, Italy.
And finally, on our panel today, we have Giacomo Falorni, who is Technical Director with Tre Altamira. Giacomo has been working with InSAR data for 20 years, ever since he was awarded a fellowship at the Massachusetts Institute of Technology to work on NASA's Shuttle Radar Topography mission data. His background includes a PhD in Earth Sciences from the University of Florence, Italy, with a specialization in engineering geology and a bachelor's in geological sciences. His geological training, combined with in-depth knowledge of InSAR, have led to hundreds of successful projects in the mining, oil and gas, urban infrastructure, and geothermal sectors. Giacomo, thank you so much for joining us today. We're so glad you're here.
Thank you, Jillian, for the introduction. Greetings from Vancouver, Canada.
All right, and now speaking to our webinar attendees today, just to let you know, you are muted and your video is off since this is a webinar. However, you can interact with our panel by asking questions at any time using the Q&A button, which is located at the bottom of your control panel. So you click on that button, it opens a window and you're able to type questions into that window. You can see all the questions that are coming in. If you see one that you like or similar to your own question, you can vote it up with a thumbs up. We are recording this webinar, so you will be able to watch it later. And then we are going to do now our first interactive portion of this meeting is we are going to launch a poll. And now this poll is going to come up on your screen. And you should see one question with 4 options. And so what we're doing here is just trying to get an idea of what is your experience with InSAR? So the question is, do you have experience with InSAR monitoring? Have you now or have you ever used InSAR monitoring in your workplace or for a research project? So this is just to get an idea of who's working with the data currently. Maybe your site uses the data, but you don't work directly with it. Maybe you've never used it, but you are somewhat familiar with the concept. Maybe you're taking the radar course, or you've not used it and you're not really familiar with it. And this is your, kind of a first introduction to what is InSAR. So I'll just give you just about a minute to go through and do that. I see all of you are doing really great. We have already 60% participation. You guys are great. All right, I think it's starting to level out here. I'll give you guys just a few more seconds. Okay, great. Thank you for your input. And here are our results. So it looks like we have a good population here, 63% of you directly work with InSAR or have worked with InSAR monitoring data. So that's really great. Another portion of you, 14%, your site uses InSAR, but you may not directly work with the data. And then we have about 22% who have not used InSAR monitoring, some familiar with and some not. So that's really great. Thank you for sharing that information with us. All right. So now I am going to kick off the question portion of our session. So what we're doing here is we've collected some pre-submitted questions through either the form that was supplied with the registration or through our radar monitoring course participants. So what we're going to do first is just some kickoff questions, and then we'll get into pre-submitted questions, and you're welcome to start using the Q&A at this point in time. So I'll start off asking some pretty big questions, but we'll be asking for high-level answers from our experts here today on these 3 questions. So starting with Jon Leighton, could you just give us a quick overview of what is InSAR?
Sure. So we're talking, of course, about satellite InSAR, radars in space that emit microwave pulses are about a few centimeters in length. And these form radar images, or SAR images, synthetic aperture radar images. So every few days, a satellite can take the same image over and over again. And for a pair of images, we can make an interferogram. So this is the phase difference between these 2 images and contains ground displacement information. And then over time, we collect many images and we take this cube of data. We can model out unwanted signals. This is what InSAR is. We're processing the data, we're removing these signals in order to just leave the ground displacement information remaining, which can cover a wide area and is precise to millimeters, typically.
Great. Thanks, Jon. And now on to Paolo. How is InSAR used for mining?
InSAR in mining is used, first of all, to get the deformation measurement or displacement measurement over an entire mine site. Okay, that's the unique capability of InSAR, to cover with a single satellite frame, a very large mine site, including all the main assets you may have at the mine site: open pit, waste dumps, stockpiles, tailing dams, and all the infrastructure associated with the mining. So if I have to tell you what kind of main use you can get from InSAR is for the early detection of very minor movements over large areas, and to identify progressive trends over those areas. And it's a very complementary tool to what you can do with other monitoring system that you may have on the ground. For example, ground-based radar or PRISM or geotechnical sensor. So it's really a complementary tool capable of covering large areas without the need to install anything on the ground.
Very good summary. Thank you, Paolo. And then Jon, considering the details that Paolo just gave us, what's the best or shortest scan time that's currently available for monitoring using InSAR in mining environments?
Sorry, Jillian, you said Jon, but I presume that was for me.
I'm sorry, Giacomo, yes.
Yes, so there's several satellite systems currently available out there. All of them have revisit time, so how frequently they scan a site, that is in the order of several days. I'd say anywhere between 8 and 15 days, let's say. You can combine some of them. For example, if you use the TerraSAR-X and PAS satellites, which each has a revisit time of 11 days, you can combine them so you get 2 revisits every 11 days. They're actually 4 and 7 days apart. So that would be the shortest scan frequency. Then if you also use them from a second orbit, so when they're traveling, these are polar orbiting satellites, so that when they're traveling from the north to the south, they're called It's called an ascending orbit when they're traveling from the from the north to the south. It's called a descending orbit. And so if you acquire images from both orbits, you can then half that time. So you can get 4 images every 11 days or 4 updates every 11 days. So that would be the absolute maximum currently available. In the future, there's new satellite systems that will be going up that will allow for even more frequent revisits and updated scan times.
Great, thank you so much. So hopefully for those of you who answered the poll that you were less familiar with that InSAR, that just gives you just a quick primer as to what is InSAR, how is it used in mining, and what type of monitoring periods can you expect to gain from InSAR monitoring. Like I mentioned in the beginning of this webinar, we do have an entire course on geotechnical radar monitoring and also one on slope performance monitoring using the experts that are in this panel. So I would invite you to take those courses to learn more details about InSAR if you're interested in more about how it works. We're going to start off with some of the pre-submitted questions, but please feel free at this time to start entering your questions into the Q&A. The GCE team is going to be sorting through those questions, and we'll be selecting questions to answer live here during this webinar. So don't be shy. Please feel free to enter your questions. So we'll start off with a topic that has been in the news lately, and this is a question that also came in as a pre-submittal. So as a safety share, InSAR can be used as an early warning tool. We know this. Recently, the Chopler heap leach pad failure has been in the news quite a lot. It is a tragic story, and it's something that we want to highlight as a safety share for things that we want to avoid in mining. We want to avoid landslides. Monitoring can help to be able to detect movement in mines, in slopes, in other structures in mining. And so the question we want to talk about here today is, does our panel have any insights on this Chopler heap leach pad failure in general? Did InSAR see any trend or acceleration? I know a lot of times when these types of failures happen, there's some analysis that's done on the data to see could it have been seen, or just any general thoughts about InSAR as an early warning tool in this type of situation. So I'll ask Paolo to start with this one, and then we will open up to our other panelists.
Thanks, Jill. So yes, this of course was a tragedy. I mean, we have seen the videos now of the different videos on these large-scale failures. Unfortunately, several people have been killed because of this, despite the fact that the site was monitored. Okay, there are at the moment ongoing investigation on the root causes of these events, so we cannot disclose that much about this. But what we can say is that there were deformation preceding this event, okay, significant deformation preceding this event, with a time frame which is compatible with the InSAR typical time scale, so several months before the failure. And there was a radar on site. The radar was mainly focused on the open pit to the side of the heap leach, but it was also covering the west side of the heap leach, and radar also detected these precursor movements. So just to say that even though monitoring systems were in place, something went wrong, apparently, no? Because people were killed. So apparently there were some identification of the issue, but not probably at the scale of the event. And this, of course, did not allow to prevent the complete access to the heap leach and to remove people from the run out of this failure. So again, it's another failure, another tragedy. We try, no? All the communities working in order to improve the monitoring practices of mine site. This mine site was having good technology, but for some reason, which to me are more related to the response plan more than probably the input data, this was not. This event was not anticipated to the scale of the failure that occurred.
Thanks, Paolo. John or Giacomo, would you like to add any thoughts to this.
Yeah, just to say that the data is very good here. I don't think there's any commercial data, but there's good Sentinel data, so medium resolution data, and the ground conditions are very good for InSAR. So, you know, it's different to say Brumadinho in those instances. It's a very arid site, ideal for InSAR. And yeah, I kind of agree with Paolo's statement. The displacement is clear. We obviously expect displacement on that kind of structure, but precursor displacement is also clear.
And Giacomo, any comment?
Not really. I think both Paolo and John have covered it well. There's nothing to add other than, you know, the monitoring tools were there, the data is there. As Paolo says, it's how you use that data that's really important. So
That's right.
Just to complement to what John and Giacomo said, it is important to mention that there was also some snowfalls in the weeks preceding the collapse. Of course, area where there was no accumulation most likely are not useful to provide displacement data in the very last part of the failure, but most likely this was covering just a small section of the heap leach. And as John said, there are very good Sentinel dataset from multiple parallel track with different angles, different line of sight, so more near range and far range. And this would be, of course, analyzed by probably several tens of research group or let's say consultants, because nowadays InSAR is available for almost everybody. Okay, so that's an important point to consider when it comes to failures like this, that there will be investigation from multiple parts and this data set will be available. Okay.
Yeah. And just to add to what Paolo was saying about the snowfall, actually, there was some snowfall. It wasn't heavy snowfall, but it probably was enough to introduce a little bit of noise into the data. And so it obviously makes the interpretation a little bit more difficult in those cases there. So the melting of the snow actually probably played a role in the failure as well. I'll just add that.
All right. Thank you so much for your insights on that. And for the person who submitted that question, we thank you. All right. Lots of questions coming in. I see some questions going into the chat and some going into the Q&A. We'll ask if you would please try to use the Q&A versus the chat. It's much easier for us to sort through the questions when they're coming in through the Q&A, if you're able. I'm going to bring up a question that we've gotten a few that are in a similar type realm. So this question came in from Christian and is asking, what is the range of displacement accuracy of InSAR? And this is similar to another pre-submitted question that we got that asked, how accurately can InSAR predict slope displacement at critical moments before failure? So if the panel could maybe touch on the accuracy of InSAR for detecting failures and how accurate is it for displacement? What level of displacement can it monitor? So I'll just allow anyone who wants to start with this. John, I see you've unmuted.
I can have a stab. There's two components here. First of all, let's talk about accuracy and precision first, because we don't normally have much to say about the accuracy of InSAR, because for a few reasons, it's not an accurate record of the height of the ground. We're not measuring really the height of the ground. InSAR will miss large events, dumping activity, for instance. There could be issues in processing which might underestimate the real level of the ground. There could be sensitivity issues which also underestimate. So it is a precise technique. It's a very repeatable technique, precise to millimeters. And that, the message I get is what geotechs mostly care about. They want to see a repeatable measurement. They want to see the change from time to time. They're not looking for some absolute number that, for instance, LiDAR or GPS might give you. And then the range of displacement is not really limited. A limiting factor is really the gradient of displacement. So you can imagine contours on a hillside that get closer and closer together. Eventually, a contour lies on top of another, and you are aliased. You can't tease this information apart. So the gradient of displacement might be smooth at first and then get steeper and steeper. There are problems you can run into, but there is no real limit to the amount of displacement, the range of displacement you could measure. Rather, it's the gradient. And the solution to that is often to collect data more frequently if you can. There are other solutions to that as well.
And go ahead.
Yeah, if I can add to what Jon is saying, he's correct. And in that, if you have a nice gradient of displacement from the edges of where it starts to move to, the area of maximum displacement, the range of motion that you can detect is quite high. As a rule of thumb, I say, typically we can get to around 1 meter per year of displacement. So we're looking at, relatively small displacements, if you like, in mining environments. If it goes beyond that range there, we typically revert to what we call it rapid motion tracking, but it's a form of displacement, of offset tracking or speckle tracking. It's also known as, where instead of using the phase of the radar signal, you use the amplitude. You track basically you track bright pixels, good reflectors on the ground of the radar signal as they move down slope, and that then increases the range of displacement that you can measure to tens of meters per year. So you can actually follow much larger movements, albeit less precisely. We're looking at the precision then is 10, 15 centimeters rather than millimeters. But when the movements are so large, that's more than enough usually. So you can extend the range. Let's say if you build into your monitoring program also the what we call the rapid motion tracking.
So leading into this next question, so talking about the range, what about the trend of the measured displacement using InSAR? Could you talk a bit about how you recognize trends for the displacement, and then also how might thresholds be determined for that movement? Giacomo?
Sure. Yeah, this is a really interesting question, because right now with these satellites, let's say we're using an 11-day revisit time, you're getting an update every 11 days. And so you typically with InSAR, you get thousands or tens of thousands or even hundreds of thousands of measurement points. So if you're getting an update every 11 days, how do you sift through that data to identify the points or the areas that are most of interest? Because you can't obviously go through each point individually. You have to have some sort of tool that allows you to identify those points that are of interest that are showing displacement. So there's what we do is just simply use what we call a trend variation algorithm that automatically sifts through the tens of thousands of points and identifies those and highlights those that do show a change in trend over the last few weeks or months. And so that will automatically highlight those points for the geotech team on the mine, so that they can focus in on those points and determine if any action is needed and what action is needed. In terms of the second part of the question, the acceptable thresholds, really those are determined locally. Obviously, different different mines and different settings, different geological settings will have different thresholds. So typically what we do is have a discussion with the geotech team, the local geotech team, and set those thresholds together based on the local conditions. And on the InSAR side, you also have to take into account, how noisy the data is. If you have a very clean and high quality, all points, your points are of high quality, then you can set those thresholds more precisely. In other settings, it might be a little bit noisier. If you're, more in a forested or vegetated environment, you might have more noise or fewer points, so you might need to adjust those thresholds slightly. But I think what we find is it's that collaborative approach where, as InSAR experts and the local geotech team, we get together and determine what those thresholds should be.
Yeah, threshold determination was a question we got from multiple persons. So it's definitely of interest. John, do you have something to add?
Yeah, the InSAR provider, there is no set method here. So I guess we can only really talk about our own approach. 3VG's approach, in terms of a threshold, is to try and estimate the noise in the data. So the noise comes from a few different sources. There is residual atmosphere, there is how well I can estimate topographic influence, and there is just coherence, right? How coherent is the data? And then for each pixel, then you can come up with a noise, an uncertainty estimate. And then when you get your displacement, you can compare that and you end up with a signal to noise ratio, and you can threshold the data based on the signal to noise. So you might find some areas with ideal ground conditions, you can measure small displacements, but they are statistically significant. And then other areas, you have to be more conservative. And that we prefer that approach because, if you just said everything below a few millimeters is junk, then you will throw away some good data and you will retain some poor data. So the noise varies everywhere and over time. So that's kind of why we prefer that approach.
And Paolo, did you have something to add?
Yeah. I think probably we are covering two different, let's say, interpretation of movement threshold, no? Because what John just said is related to what is what we consider, no, the minimum reliable level of displacement we can measure, and so I fully align with what he was saying. Probably what Giacomo was referring to is threshold in terms of response plan. Okay, so what are the let's say threshold of velocity or displacement we can define to let's say raise our hands and say, okay, here there could be something to be investigated. From my point of view, of course, the first question is related to the signal to noise ratio and so on. So no doubts. The second question could be a little bit tricky because, first of all, I mean, InSAR is not supposed to be used as let's say a real-time early warning system. Okay, so InSAR data in the best case can be received every 4-7 days. Okay, so this of course prevent the use of InSAR as a real-time system for alarming purpose. But of course, and this is good that we have in this question the first part, it could be a good tool to identify areas where there are ongoing acceleration, so where progressive trends are occurring. And then the first part of Giacomo comments, in my opinion, is very good. We have to look for areas where there are change in the trend. You can do it with multiple algorithms. Okay, one option, for example, we are exploring since several years is to run inverse velocity over all the time series. So if you have 1 million of points, you can run with the modern cloud computing capabilities inverse velocity in order over all the million points in order to identify those points that are showing an acceleration matching with the inverse velocity model. And of course, this provide also some input on the how far we are, at least based on InSAR, from the possible intersection date of the linear inverse velocity with the time axis, which is an indication of the possible time of collapse. I think that when it comes to threshold, I don't, on InSAR, I don't rely that much on absolute threshold. I mean, apart from what we get from inverse velocity, but I rely a lot on deformation threshold, because InSAR can also be used to calculate angular distortion, horizontal strain, and this kind of parameter provide the differential, let's say the spatial pattern of displacement, which we call deformation, in terms of millimeter per meter. And these are nowadays becoming also for modeling the new trend to, instead of calculating the factor of safety of the probability of failure, deformation, absolute deformation threshold are becoming really relevant. So this is something that we can work on to provide input to the InSAR user from the use of InSAR to define where critical areas are developed.
So some questions coming in related to predicting failures and setting alarms. Would you like to touch on the prediction of failures using InSAR? As Paolo mentioned, it's not a real-time monitoring tool, but are you able to predict failures, and is there some accuracy you could put to that? Yeah, I can try to start and then pass the floor to the other speaker. Now, from my point of view, you have to use this technology to try to identify, to predict what we call incoming failure conditions. I mean, areas where there are trends potentially associated with a slope collapse. Of course, the fact that you can, if you can precisely predict or not the time of failure, is a function, to my experience, of the failure time scale. So what is the time from the onset of the acceleration to the failure? And this, of course, can be different depending on the failure mechanism you are dealing with, depending on the material you are dealing with. You may deal with very brittle, fragile material where failure may occur with limited deformation and a very small amount of time, or with very plastic failures lasting months or years before failing. So we cannot, let's say, cover the entire range, but I'm sure that, especially for large-scale failure, InSAR can be a very good tool to initiate the prediction of the failure. Then, of course, in the last stage of failure, you need a real-time tool like radar, okay, or GPS or PRISM. That's my experience, and I always, let's say, recommend InSAR user to try to analyze InSAR data with this specific scope. Of course, expecting that there will be a range of failures in terms of size and in terms of, let's say, temporal evolution not covered by InSAR. Yes, all tools in the toolbox, and this is one of the very important tools in the toolbox. Great. Any other comments on this, John or Giacomo?
Yeah, I mean, Paolo's the expert here, really, you know, in terms of inverse velocity. And but what I will say is that right now, our sampling is maybe 11 or 12 days, right? Is common. And that is not great if you're trying to sort of predict these trends and do these kinds of analysis. But as we go forward, we're hopefully going to see that reduce, and there are commercial constellations promising a day repeat or even under, and that could change the game in terms of how well we can use predictive type algorithms.
Giacomo?
Just to add to what both John and Paolo are saying, I think with the strength of InSAR is, you know, the early detection of those areas of incipient movement. So it's certainly not, as both speakers have highlighted, a real-time tool just because of the sampling time. But it can give, what it does provide is an early detection of areas that are starting to move, so that then, if they can continue moving and accelerating over time, you get both, you can see the trend in time. You can also see the area of displacement, so get an idea of the size of the area that's, starting to move. And then if that trend continues, you can bring in real-time monitoring systems like ground-based radars and others, so that basically, you can cover a wide temporal scale from, if you're lucky, you can catch it months in advance and take, remedial measures. As Paolo was saying, it also depends on the materials. If it's a very brittle rock, you might not have enough, there might not be enough precursor movement to catch it early enough to do anything, at least from an InSAR point of view. But certainly in some cases, there's that curve that you can see in the development of the acceleration over time.
So with those slower moving failures, then can you set alarms for when a measured displacement goes above a certain threshold? Is that a practice that's done with InSAR?
We do it. We do this. We can define, for example, R-square regression coefficient threshold, okay, and a certain time from the time of the prediction to the time of the intersection date with the linear extrapolation of the inverse velocity, and a certain number of contiguous pixels, okay, because we cannot rely on single pixel, but we need to have at least a minimum number of a cluster with a minimum number of points. So it can be done. It can be also used normal, let's say, for example, threshold of velocity if we have some insight on the mechanism and we know that there could be some issues. Of course, as Giacomo said, in the early days, don't expect to be able to follow the final part of the failure, because with the current satellite, we have this limitation. Again, the range of failure time scale we will be able to cover will be larger in the forthcoming years, when new satellite with a highest acquisition frequency will provide data. So that's something that we are sure that it's important to start now, because the situation will quickly improve in the forthcoming years.
Good. John?
Yeah, just to mention that, I agree with, the caveats about we're not sampling frequently enough, really, to commonly use this as an alarming type of critical monitoring tool. But when people do set these alerts, commonly it's done in integration platforms that are pulling data in from a number of different sources. And, I think that's, the most common way to sort of set these kinds of alerts is using an integration software.
All right. Giacomo?
Yeah, just very shortly to add, this is a request that comes in more and more frequently now. We do get this type of request from the geotech teams. So it is something that, we're currently on our online platform. We don't have it developed yet, but it is one of the next features that will be coming up, is to be able to set certain values initially based on cumulative displacement, as Paolo was saying, not on the deformation rate or displacement rate, but just you can set certain values on cumulative displacement. Once that value is reached, an automated alert is sent out to the geotech team at that point.
Good. So we've talked a lot about slope displacements for preventing landslides. We did get a few questions coming in on subsidence management. So also deformation, but a bit different nature. So the question is, can InSAR be used for subsidence management? For example, like a crown pillar, monitoring crown pillar in underground mining. So John, I believe you might have a presentation on this in the course, a case study related to subsidence monitoring. Am I correct on that?
Maybe. But what I will say is that any displacement that expresses on the surface can, in principle, be measured as long as there is coherence. You know, we're not looking underground, obviously, but if it expresses on the surface, then sure, it can measure the displacement. Underground mining can cause InSAR problems if it becomes really fast, or if the gradient, remember we talked about the gradient, becomes too steep, then we might use speckle tracking, offset tracking, these kinds of amplitude-based approaches to monitoring the displacement.
Any other experiences from Giacomo or Paolo with InSAR being used for subsidence monitoring management?
Yes, I mean, I think this is almost bread and butter, or how InSAR almost got started was for monitoring subsidence. We had an interesting project that ran for a number of years where there was a town in Wyoming, actually, that was, they had started a coal mine, I believe, back in the late 1800s, actually. And then they had, back then they just followed the seams, and the mine development itself was rather chaotic, went in all directions, was never mapped. And eventually, and the town, at the same time, the town above it was expanding and growing. So eventually the town ended up, a large portion of the town ended up being above the coal, the mine itself, let's say. And so obviously what happened then, they started to see subsidence with damage to the buildings and so forth. So the InSAR was used there to identify those areas most affected by subsidence, and actually go in and grout or fill the voids as much as they could to prevent further subsidence in those specific areas. So there it was used, as almost a diagnostic tool or an investigative tool to identify those areas that were starting to show movement, and to remedy that, provide remedies for those areas there. And we've had numerous projects of that type. This is where the millimeter precision of the technology can really help in these cases here.
Yeah, on top of this, I can also mention that InSAR can be very useful when it comes to monitor block caving areas, where subsidence, of course, is creating a crater, which with displacement of meters, of several meters in some cases. And of course, InSAR is the ideal technology to cover this area, including the phase-derived displacement and the speckle tracking derived displacement, because this can really help to identify the areas where the gradient is developing and where cracks are developing. Okay, this is really a unique capability of InSAR, and also by combining InSAR data, it could be used, for example, in subsidence areas where urban settlements are built on top, to calculate the potential damage on buildings and infrastructure. So this is a pretty unique capability of InSAR, and I think there are still a lot to do to fully exploit the data we can get from InSAR on this type of application.
If I can add to that, Gillian, and Paolo brought to mind a great example of block caving and measuring the subsidence crater. There's a mine we're currently monitoring where they do have block caving, and they initially had survey benchmarks within the crater area, but the displacement got to be so large that they started to lose these monuments. And so they've now completely shifted to, because these are areas, these craters are no-go zones. No one is allowed on them because it's too dangerous. The ground moves too rapidly, basically. So they couldn't go back in and install new benchmarks. So what they now completely rely on you know, what, as I said, what we call rapid motion tracking, a variation of the speckle tracking, to monitor that area and to measure. And then they integrate that, so they have an idea of how fast the ground is moving in the subsidence crater, how rapidly it's expanding. And also now you integrate that then with the InSAR per se, the more precise, you know, the actual InSAR technique around the edges, so that you can very clearly see, you know, the progression of displacement laterally as well, with millimeter precision around the edges.
All right, great. The hour is flying by. I think we may have to do another one of these with all the questions that have come in. Everyone really is interested in InSAR. It's great. I want to talk a little bit. We've had a number of questions come in either pre-submitted or through our live feed currently about the limitations of InSAR monitoring where it cannot be used well. And specifically, I'm going to just touch on a few questions that come in that might be somewhat related. So firstly, does slope orientation have any impact on deformation resolution? We know that with the side viewing orbit that sometimes we are unable to image certain slopes based on the passes north-south, south-north. So any other comments on slope orientation and the impact on, is that a limitation for InSAR? Jon.
Yeah, so it's important to remember that the satellite is approximately orbiting north-south, and it's looking at right angles to that. So it's not really looking north and south, it's looking east or west. So when you have horizontal displacement that's moving north-south, it's not very sensitive to that displacement. In terms of slopes, if we had a north or south facing slope, it would detect the vertical component to that, but not the sort of northerly or southerly component to that. So it wouldn't pick up as much displacement as it would, say, on an east or west facing slope. And then the slope, if it becomes steep enough, light might not even see it, right? It could become in shadow. If in the other scenario, if the slope faces the satellite, that also is a problem because of radar geometric effects. So the best solution around these common situations at mine is to monitor the site from both east and west looking directions, and that will help you build, you know, a bigger picture of the slopes on the site. Most areas could be completely covered as long as the ground conditions allow.
Well said. Well, anything to add, Giacomo?
Yes, as Jon said, the slope orientation is very important. North-south facing. Currently, with the current satellite systems, we can't, you know, we can measure the vertical component. The topography is another factor, you know, as Jon said, how steep the slopes are is important. Another important limitation is presence of vegetation. With most of the current satellite systems out there, they're not able to penetrate through forest canopy. So if you have, you know, an area that's heavily vegetated, you probably will get a limited number of points or measurement points. Snow is also a limiting factor. If you have snow for part of the year covering, you know, your site, then you might not be able to get measurements during that during the winter months, let's say. It also depends on the characteristics of the snow. We've found that if it's very dry snow, so in colder climates, you can actually see through a limited amount of snow cover. So we've been able to get measurements even in the winter months in those situations there. If it's wetter snow, so typically the results even in areas with dry snow, you get worse results, say in the spring, because the snow becomes wet, and that's when the water content increases. Then you have less penetration of the snow. the way to get around snow is you can either, if you don't get anything during the winter months, is just to do what we call a snow-free processing. So you process during the months when there's no snow on the ground. And regarding vegetation, the remedy, where I think the whole InSAR community is excited about the launch of NISAR, which is it'll be the first US satellite or US owned civil satellite, let's say, for monitoring for SAR purposes for InSAR. And so NISAR will have a longer wavelength. It'll be an L-band satellite. And so that should give much better penetration of canopy and vegetation in general. So to really extend, the areas that can be monitored with InSAR. And a final comment on the north-south component, there's new satellite systems that plan to have inclined orbits. So instead of being, approximately north-south, as John mentioned, they will be inclined to say around 45 degrees. And so that will give them equal sensitivity to the east-west and the north-south component. So, maybe 4 years from now, we might be able to also start monitoring the north-south component of movement as well.
Very exciting. All right, we have just 2 minutes left. If our experts enjoyed today's session, maybe we'll be able to get them back for another session, because we have a lot of questions that have come in that we have been unable to address. If you are a student currently in the radar monitoring course, I'll invite you to please move your questions over to the discussion board, and we'll directly connect you to the experts here today to get your questions answered. I want to give a tremendous thank you to our panel today that have volunteered their time to be here. We appreciate you so much. What you're doing for Knowledge Share for the community is magnificent, and I'm sure not only we appreciate it, but all our participants today as well. I see lots of clapping hands coming up on our screen. And then, as promised, here again is the slide. If you are interested in registering for our geotechnical radar monitoring course, it's currently in session. Also coming up in April, we'll have our slope performance monitoring course that covers not only radar monitoring, but all other types of monitoring for slopes. So thank you so much, Giacomo and John and Paolo. Couldn't appreciate you more.